Good morning. Okay, I think it'll be about a week and a half, and we'll be done physics, which means we'll be done our optics unit. This week is going to look probably closer to physics, the closest to physics that you've actually seen so far in this course, which means we're doing some equation work today. It's mostly going to be a note and then practice questions from the textbook. What I am going to suggest, if at all possible, and if you can, it's fine, we'll work out something, is that you come to a Google Meet this week. I prefer tomorrow. It's at 12:30 so that I can talk to those students specifically who are taking physics about a few pieces. I think it would be to your benefit. Okay, so let's get started on the note today, and I'll leave details all about that on your post on Classroom. Okay, so here we go. The title for today is Thin Lens Equation. Thin Lens Equation. Okay, and I'm going to rely on your math skills a bit here. And I anticipate for some of you, you'll find this more challenging than others. So you might need more individual support. You might want to ask me questions. You might want to come to a meet so we can actually chat with each other back and forth to work through this. All right. Okay, so I'm going to start with what the equation is that we're actually going to learn to use. Actually, back up here for a minute. So far, whenever I've given you a lens, whether it's converging or diverging, you've done a ray diagram with it. So you have the lens, you have the focal point of the lens, and then we've used an arrow in every situation so far as our object and tried to find out what the image of that arrow would look like. Would it be on the other side of the lens? Is it right side up? Is it upside down? Is it real? Is it virtual? All of those kinds of pieces. What's its size? Bigger, smaller than the object? And we draw them all out by hand. So that works. And you can be super precise about that. If we were in the classroom, we'd be using rulers. We'd be being really detailed about measuring the correct distance to place the object before we draw the lines. We'd be super accurate about when the lines cross, tracing that back to the principal axis, measuring perfectly what the height of that image is, measuring where the image is in relation to the optical center of the lens. All of that would be mathematical. All of that would be quantitative. So far we've just done qualitative because the way we're learning. So when you get the image, you describe it using the acronym SALT. So it's size, it's attitude, it's location, it's type, and none of that has been quantitative, which means none of that has been measured. But we could make it quantitative, where instead of just saying it's larger, you would actually provide a height in centimeters, like 4.2 centimeters would be the actual size of the object. Location wouldn't just be generally like on the same side of the lens between the lens and F or something like that. It would be a measured distance and we would pinpoint that. So that is one way to find where the image is, to actually do these drawings, which are quite accurate, and then take your measurements off the drawings. Another way is to use an equation, which is what I'm teaching you today. So there's two methods to use. Both should get you to the same end result. So that's how you know you're doing them right, is that no matter which option you choose, you should be getting the same answers. So the equation, as the alternative to doing a full ray diagram, is called the thin lens equation. And it is 1 over F equals 1 over little d subscript O plus 1 over little d subscript little I. So the reason I want to talk to the kids who are going to take physics is because physics is full of equations and variables and pieces like that. And I just want to make sure we have a little chat about that, what you can and can't do, and if I need to provide you with some further practice. Okay. All right. So let's break down what each of these things means. F is the focal point of the lens. Focal point of the lens. So when we do our diagrams, we have the principal axis, we put the lens on it, and then because it's a lens and light can go through lenses from either side, we put a focal point on each side of the lens, okay, whether it's converging or diverging. Little d stands for distance. And so both of these are distances. The one with the subscript little o is distance of the object. And that is from the lens, from the optical center of the lens. Okay. So I'm going to put here from lens. So where that original arrow is. It's always been an arrow in our diagrams because arrows are easy to draw and we get all the information we need about the image, for example, whether it's upright or inverted with an arrow as well. But the object in real life might be a person, okay? Anything you're looking at, planet, a section of a leaf, whatever it is, okay? This is once again distance, but you may have figured out the little I stands for image. Distance of image, once again, from that optical center of the lens. From the lens. And this works with thin lenses. Okay, so not great big pieces of glass, but the thin pieces of glass that we're used to seeing and working with in microscopes, telescopes, cameras, all that kind of stuff. All right, so this is going to tell you several things that a full out picture would also tell you. So before we do too much more, I want to write down over here the two differences between diverging, converging, and their alternate names, because the textbook tends to use concave and convex quite a bit. So just when you're doing the practice questions, to make sure you know which kind of lens they're talking about. And then I'm going to do a sample problem with you, same one from the textbook, and walk you through how I would solve it and how you get to the answer, and then we'll practice from there. Okay, so let's start with the converging lens. It's the first one we talked about. Converging lens, okay, also known as convex lenses. I'm just going to move my elephant out of the way. Okay, convex lenses. So these are the ones that look like this, just to review it. Bigger in the middle than they are at the top and the bottom. This would be their axis of symmetry if I drew a line right down the middle. It was the principal axis right here. The optical center is right in the middle of the vertical, right in the middle of the horizontal, okay, right there at the center. So for these kinds of lenses, there'll be a focal point on this side, focal point on this side. And then when the ray comes in, if the ray came in from up here, idea is it heads towards that. If a ray came in from down here, it would head towards that. Everything is converging in here. So these ones have a positive focal point. I'm going to hit here. Have a positive focal point. And location of image varies. And it always varies because it depends on where the object is in relation to the focal point. But what I mean by that is, if my object is over here on this side of F, when I draw the ray diagram, it's going to show up upside down over on the other side of the lens somewhere. It's going to be a real image. Okay, that is always going to be the case. The general properties of the image will always be inverted, which means upside down, and real, if the object starts out past the focal point out here. If I move the object to and sit it right on F, I won't be able to get an image because the way the light rays work, they will never cross. As soon as I come inside of F, so I'm between here and the lens, the light rays won't converge over here. I have to trace backwards and I will get a virtual image that is upright on the same side of the lens as the object. Okay, so that's why it says location of image varies. It can be on the other side of the lens or it can be on the same side of the lens. It all depends on where you put your object to start. Okay, diverging lens is what I did right at the end of the week, and there's only one kind of ray diagram because the image will always show up with the same properties. So converging lenses are also called concave lenses. They are the ones that look like this, cave in at the middle. That's why it's kind of easy to remember concave. They also have a focal point on either side because they're made of glass or plastic, something that's transparent. Light can go through both ways. So in this case, when a light ray comes by from an object somewhere, no matter what place it is going to not come towards F, but go on a trajectory which sends it out. And that trajectory out is based on if I'd had a ruler and I went like this, I traced it back, it would go through F. Okay, so these ones, if I did another ray, it came in here, it would diverge out this way from F, trace back here. Where all those light rays are coming together are on the same side as the object. So these ones are said to have a negative focal point. Focal point. Okay, and location of the image is always going to be what we call negative. It's always going to be on the same side. Okay, location of image is negative. And I'll explain what that means in relation to the equation. So that might make sense a little bit more once I do the problem. But to be negative, it means it's on the same side as the object. So it's always virtual. And what we learned here is whenever you make an image with a diverging lens, it's always smaller, it's always upright, it's always virtual, and it's always on the same side of the lens as the original object. Okay, and for equation purposes, you know it's on the same side of the lens as the object because it's going to be negative when we solve for the formula. Okay, so you're going to have to bear with me here for a minute. We're going to write out the question so you have it in your notes. I'm going to look at my paper so I don't screw it up a bit here on you. All right, so let's do, okay, practice problem. We will call this. Right, and I'm going to move my page up. Okay, I'll try and write neat so you know what I'm writing. This is a question from your textbook. So, magnifying glass is held 2.00 centimeters above a page. So first of all, this is physics. Physics is all about significant digits, units, accuracy, all those pieces. So this is a measured perfectly 2 centimeters above a page. What you know about magnifying glasses from what we've talked about before is that the whole point is to make the image bigger than the object. It should be upright. You don't want to be trying to look at something and have it blown up for you so you can see it and then it's upside down. And it's virtual. You can't capture what you're seeing through the glass on any kind of screen or page, paper, anything like that. Okay, so it's virtual, the image. So if the virtual image is 3.60 centimeters away, what is the focal length of the lens? So with this equation, you will always have two pieces of information and you'll solve for the third. So back to this, I have F, distance of object, distance of image. You always get two pieces so that you can solve for the third, the unknown. In this case, we are looking for F this time. Most of the time, you're looking for distance of image. So the next question I'm going to do with you is going to be looking for a distance of image instead. So I'm going to draw this out for you a little bit because I think it might help to see it. So let's do like a principal axis here. Okay. And magnifying glasses, as we know, have converging lenses. Converging lens here. So you could draw this whole thing out with a ray diagram. You'd put your converging lens. You would have to you have to work backwards to do it. I'm not going to walk you through it right now. I don't want to put too many things all in the same lesson, but if you wanted to, you could. Also check your answer. Once we get the focal point, you could draw it all out and see if the image falls in the right spot. But so like I said, all these methods can overlap with each other. Okay, so the magnifying glass is our lens, and it's 2 centimeters above the page. The page is the original object. So I'm just going to do, this is not going to be to scale. Here's the page. Okay, the magnifying glass is above the page. And I know that this distance from here to the optical center of that lens is 2.00 centimeters. Okay, I know that I'm going to get an image for this, which is larger, is virtual, same side of the lens, all that stuff. I'm not going to do this to scale. So let's do, okay, here's my image, and I have the information that from here to this image, DI equals 3.60 centimeters. Okay. And I'm looking for what is the focal point of this lens. Okay, where is it? And I don't know that just yet. So how you should always answer these problems is how you've been trained, hopefully in science before, to answer questions. Start by writing down your givens. So what are the things you know? So givens. I know DO and I know DI from the question. So the distance of the object, DO, equals 2.00 centimeters. Always keep your units. And DI equals 3.60 centimeters. Okay. Now, because it's on the same side of the lens as your object, this should be negative. Okay. Think of it as here's my distance, and now I'm behind it, same side of the lens. So this negative piece is going in because it's the same side of the lens, like I said to up here. Location of image is always varies here, but on this side, we talked about it being negative because it's going to show up on the same side as the object. So it's because it's virtual. So I can write a little note here. This, because image is virtual. And it told us that in the problem. Okay, so even if you didn't know that by what you generally know, as soon as you see virtual image, you should know that that should be negative. Okay, and then our unknown, just writing out the method for problem solving here, is F. So F is our question mark. Sometimes they call this required. Okay, and then the equation we're going to use to the next step would be, I'm going to put here equation I'm going to use, just show you what I'm thinking, is 1 over F equals 1 over DO plus 1 over DI. And then the next thing I do is I substitute. Probably going to run out of space here. I'm going to squeeze. So 1 over F equals 1 over DO is 2.00 centimeters plus the DI, which is 1 over negative 3.60 centimeters. And I'm just going to draw this up here. Solve. You can convert to decimals if you want. Solve this however you want, whatever your math skills provide you with the ability to do. If I put 1 divided by 2 in my calculator, it converts to 0.5 centimeters. If I do 1 divided by negative 3.60, it comes out to minus negative 0.2778 on the end centimeters. So 1 over F is going to equal 0.222 centimeters. And then there is a button on your calculator for most of you. It might look different. For some of you, the button on the calculator looks x to the negative 1. For some, it looks like F equals, I think it's F equals 1 over x. These are calculator buttons. Okay. So that's the easiest way to see that F equals 4.0 4.5 centimeters. So the focal length, there's other ways to convert this 2 to 4.5, but there's a calculator button that will do it for you. The focal length is, just doing a final statement, 4.5 centimeters. Okay, so how you could double check this if you wanted to was to draw a converging lens to a focal point of 4.5 centimeters, put your object down, do the ray diagrams, see if your image lands at 3.6 as a checking. Okay, I'm going to leave some textbook questions to allow you to practice that. I want to do one more problem with you though before I stop the video. So I'm going to move this page and we'll do another practice problem, one that looks for finding out properties of the image. Practice problem. Okay, so write it down. A converging lens I know some of you are not happy campers right now. Okay, a converging lens, and maybe some of you are like, love it, has a focal point, so I'm just going to put F, of 60.0 centimeters. A candle is placed 50.0 centimeters from the lens. What type of image is formed and how far away from the lens is it? Question mark. Okay. So you could do this by ray diagrams. We're going to use it using our mathematical prowess and skills. So once again, I'm just going to draw a little visual of this so you can picture it. We have like a principal axis. We have a converging lens along that axis. And I have a candle. And the candle is 50 centimeters from the lens. So I am going to put my candle here, my little flame on top. And from the center of there to the candle, the DO equals 50 centimeters, 50.0 centimeters. Okay. I have another piece of information. You only need two pieces of information, which is what F is this time. So F is 60 centimeters, not to scale. So from the center of this lens over here, focal point, it should be the same distance on the other side, focal point, that distance from the center of the lens to F is 60 centimeters exactly. Okay, so I could, like I said, draw this by ray diagrams. I also, if I've practiced enough ray diagrams, know that if I have a converging lens and my object is between the lens and F, I'm actually going to get a virtual image. It's going to end up on the same side of the lens. It's going to be right side up. And yeah, right side up inverted, virtual. Okay, so let's see if we can confirm that with the math. So I'm just going to write, I'm not going to write given and required and all that. I'm just going to do it. So start with what you know. So I know that from the question, F equals 60.0 centimeters. And you don't have to sketch out a picture. I just like to visualize it, but you can just go right to solving. We also know the distance of the object. We were told it's 50.0 centimeters. And what we are required to find out is the distance of the image. And when we find the distance, we'll also learn if it's real or virtual, whether it has a plus or a minus with it. The equation, the only equation you know to use so far is this, the thin lens equation. 1 over F equals 1 over DO plus 1 over DI. Okay. Next thing to do is then start substituting. So I know this is going to be 1 over 60.0. And this is centimeters, equals 1 over 50.0 centimeters plus 1 over di. Di is my unknown, the thing I'm solving for. So you can rely on your skills to start solving this in any number of ways. I'm going to convert to decimals and then go from there. So 1 divided by 60 is going to come up 0.016 repeating. So I'm going to keep a couple sixes and then round to a 7 here. 1 over 50 comes to 0.02. And then I have this still. Okay, so what I'm going to do is I'm going to move I'm going to collect these pieces so that di is isolated. I'm trying to get di on its own. So I'm going to subtract both sides, 0.02 from both sides. So I'll show you that, 0.01667 centimeters. Bring this over, minus 0.02 centimeters equals 1 over di. I'm just going to do that then, and that comes out to negative 0.00, and then 3 is repeating. So I'm just going to hold 3. Oh, sorry, I'm off the page. Okay. Equals 1 over di. Now, there is that inverse reciprocal button on your calculator. So I'm going to just put di on this side because I want to finish with my unknown here and my answer here. When I hit that button, you don't have to include the negative, but I know it's going to be negative, and I will find out this is 300, and I know I'm working in centimeters. So what does this tell me? This tells me that the image is 300 centimeters from the center of the lens. The negative tells me it's on the same side as the object. It's virtual, so it's way back here, okay, is where that image is going to be. So the first part says what type of image is formed. So the image is virtual. I know that because of this negative. Okay, that means it's on the same side of the lens as the object. Second part is how far the lens is it. It is 300 centimeters from the lens. Okay. Now, if you ever happen to do a question and the object is on the focal point, you're going to do all your math, get to a point, and you'll get error when you go to the last step. That's because there is no image. So don't worry about that. So that's a lot of new skills for today. Like I said, I'm going to leave some practice questions from your textbook. And then for all those of you who are going to do physics, I would really like to see you in a Google Meet so that we can talk a little bit more about how this is going for you and make sure you're feeling comfortable with what this kind of stuff looks like. All right. So that's where I'm going to leave it today. It felt like math class today, didn't it? And we will catch up with each other later this week. All right. Take care, my peeps.